Picture this. Right now, at this very moment, there are photons hitting your eyes that have traveled for over 13 billion years. They've crossed an expanse so vast that if you tried to count the miles, you'd run out of atoms in the observable universe before you finished writing the number. And here's what will absolutely shatter everything you think you know about reality. NASA's James Webb Space Telescope just found something at the edge of the universe that shouldn't exist. Something that breaks our fundamental understanding of physics. Something that suggests the Big Bang might not have been the beginning at all. I'm talking about galaxies, but not just any galaxies. Massive, fully formed, impossibly mature galaxies sitting right at the edge of observable space and time. Galaxies that, according to every model we have, every equation we trust, every theory that's been tested for a century, should not be there. They're too old, too structured, too perfect. It's like finding a skyscraper in a world where concrete was just invented yesterday. What NASA found doesn't just challenge what we know about the early universe. It threatens to topple the entire cosmological house of cards we've built over the past 100 years. And the implications, the real implications that nobody's talking about yet, suggest that everything we think we know about existence itself might be fundamentally, catastrophically wrong. Stay with me for the next 3 hours, because I'm going to take you on a journey to the absolute edge of everything. We're going to travel 13.8 billion years back in time. We're going to explore discoveries so recent that some of the papers aren't even peer-reviewed yet. We're going to meet the scientists who are quite literally losing sleep over what they're seeing. And by the end of this, I promise you, you'll never look at the night sky the same way again. Before we dive in, do me a favor. Smash that like button, because this video took months to research. And subscribe, because we're going deep into the most mind-bending discoveries in science. Also, drop a comment telling me what country you're watching from, and what time it is there right now. I'm curious to see how far across the globe this cosmic revelation is spreading. Let's begin at the beginning, or what we thought was the beginning. You've heard of the Big Bang, right? Everyone has. It's practically common knowledge at this point. 13.8 billion years ago, everything that exists was compressed into an infinitely small point. And then suddenly, explosively, it began expanding. Space itself stretched, time began flowing, matter condensed from pure energy, and here we are today, the descendants of that primordial cosmic explosion. Simple story, clean, elegant, and potentially completely wrong. But before we dismantle this beautiful theory, we need to understand what we thought we knew, because you can't appreciate how revolutionary these new discoveries are without first grasping the orthodox view of cosmic history. So let's build this foundation together. The Big Bang theory, first proposed by Belgian physicist Georges Lemaître in 1927, and later refined by George Gamow and others, isn't just some wild speculation. It's supported by 3 massive pillars of evidence. First, the universe is expanding. Edwin Hubble proved this in 1929 when he discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're moving. Think of it like dots on a balloon that's being inflated. Every dot moves away from every other dot as the balloon expands. That's our universe. Second pillar, cosmic microwave background radiation. In 1964, Arno Penzias and Robert Wilson accidentally discovered a faint glow of microwave radiation coming from every direction in space. This wasn't radiation from stars or galaxies. It was the leftover heat from the Big Bang itself, cooled over billions of years to just 2.7 degrees above absolute zero. It's literally the echo of creation, still reverberating through space. Third pillar, the abundance of light elements. The Big Bang theory predicts exactly how much hydrogen, helium, and lithium should exist in the universe. And when we measure these elements, the numbers match the predictions with stunning accuracy. 3 independent lines of evidence, all pointing to the same conclusion. The Big Bang wasn't just a theory anymore. It was practically fact, woven into every textbook, every planetarium show, every documentary about space. But here's where things get interesting, and where most documentaries stop because they don't want to complicate the narrative. A Big Bang theory also makes very specific predictions about what the early universe should look like. And this is crucial, so pay attention. After the Big Bang, the universe was incredibly hot and dense, just a soup of subatomic particles. As it expanded and cooled, these particles began to clump together under gravity. First, they formed simple hydrogen and helium. Then, after hundreds of millions of years, these gases collected into the first stars. These weren't like the stars we see today. They were massive, unstable, short-lived giants made purely of hydrogen and helium. When these first-generation stars exploded as supernova, they scattered heavier elements, carbon, oxygen, iron, throughout space. These elements then collected with more hydrogen and helium to form second-generation stars. And gradually, over billions of years, these stars organized into the first primitive galaxies. Notice the keyword there, gradually. According to our models, galaxy formation is a slow, stepwise process. You don't just get galaxies overnight. You need time, lots of time. Our best simulations suggested it should take at least 500 million to 1 billion years after the Big Bang for even small, primitive galaxies to form. This brings us to the concept of cosmic time and how we actually observe the distant universe. Here's something that will fundamentally shift how you think about space observation. When you look at distant objects in space, you're not seeing them as they are now. You're seeing them as they were when the light left them. Light travels at 186,000 miles per second, which sounds instantaneous, but over cosmic distances, it means we're looking back in time. Think of it like this. Imagine you're watching a live concert, but you're standing 10 miles away. Sound travels much slower than light, so you'd hear the music about a minute after you see the performer's movements. Now, scale that up cosmically. When we look at the Andromeda Galaxy, 2.5 million light-years away, we're seeing it as it was 2.5 million years ago, when our human ancestors were just learning to use stone tools. The farther we look into space, the farther back in time we see. This is why powerful telescopes are essentially time machines. And this is exactly what makes the new James Webb Space Telescope so revolutionary and so disturbing to cosmologists. Launched on Christmas Day 2021 and fully operational by mid-2022, the James Webb Space Telescope isn't just bigger than Hubble. It observes the universe in a fundamentally different way. While Hubble primarily captures visible and ultraviolet light, JWST specializes in infrared. And here's why that matters. As the universe expands, light from distant objects gets stretched to longer wavelengths, a phenomenon called redshift. Visible light from the most distant galaxies has been stretched so much that it's shifted all the way into the infrared spectrum by the time it reaches us. This means JWST can see farther back in cosmic history than any telescope before it. It can peer into the cosmic dark ages, that period after the Big Bang, but before the first stars ignited. It can observe the universe when it was only a few 100 million years old, barely out of its cosmic infancy. And this is where everything goes sideways. Scientists expected to see primitive, small, irregular clumps of stars when they looked at this early epoch. They expected to catch galaxy formation in the act, to witness the gradual assembly process. What they found instead stopped them cold. But before I tell you what they saw, I need you to understand just how shocking this is. And to do that, we need to talk about what a mature galaxy actually looks like, and why finding one in the early universe is like finding a Boeing 747 in ancient Egypt. Let me paint you a picture of cosmic evolution that astronomers spent decades building. It's a picture that, until about 2 years ago, everyone believed was essentially correct. In this picture, The early universe is messy, chaotic. After the first stars form around 100 to 200 million years after the Big Bang, they start to gravitationally attract each other. Small clumps of a few thousand stars form first. These proto-galaxies are irregular, lumpy, asymmetric. They don't have the elegant spiral arms of the Milky Way or the smooth elliptical shapes of mature galaxies. They're more like stellar nurseries, messy and disorganized. Over hundreds of millions of years, these proto-galaxies crash into each other, merge, and gradually build up into larger structures. Each collision and merger takes time, millions of years for the systems to settle down and reorganize. Slowly, very slowly, the first true galaxies emerge. But even these are still relatively small and irregular by modern standards. It takes billions of years for the majestic spiral galaxies and massive elliptical galaxies we see in the local universe to fully form. Our own Milky Way, for instance, didn't achieve its current structure until about 8 or 9 billion years after the Big Bang. That's over half the current age of the universe. This gradual assembly picture was supported by decades of observations. When astronomers looked at galaxies at different distances, and thus different cosmic times, they saw exactly this progression. Distant galaxies, seen as they were billions of years ago, looked smaller, more irregular, less structured. Closer galaxies, seen in more recent cosmic epochs, looked more mature and organized. Perfect. The observations matched the theory. Computer simulations backed this up. When researchers ran detailed simulations of galaxy formation, starting from the conditions immediately after the Big Bang and letting physics play out, the virtual galaxies evolved slowly, just as expected. No surprises. The universe made sense. Now, enter the James Webb Space Telescope with its unprecedented ability to peer deeper into cosmic time than ever before. The scientific team, led by astronomers like Tommaso True at UCLA and Dan Coe at the Space Telescope Science Institute, pointed JWST at a patch of sky that Hubble had already studied extensively. They wanted to push beyond Hubble's limits, to see the very first galaxies forming in that messy, chaotic early universe they expected. The first images came down in July 2022, and I want you to imagine the scene. Dozens of astronomers gathered around computer screens, waiting to see the dawn of cosmic history. They're expecting to see dim, small, irregular smudges of light. Primitive proto-galaxies just beginning their long journey toward maturity. What they saw instead were massive, bright, clearly structured galaxies, lots of them. Some appearing to exist just 300 to 400 million years after the Big Bang. The room went silent, then erupted, not with celebration, but with confusion and disbelief. These weren't supposed to be there, not at this cosmic epoch, not looking like this. Let me give you a specific example that illustrates just how bizarre this is. JWST discovered a galaxy catalog designated as JADES G-CZ 130, existing approximately 330 million years after the Big Bang. This single galaxy contains hundreds of millions of solar masses worth of stars. It shows signs of structure, of organization. According to every model we have, building a galaxy this massive should require at minimum 500 million to a billion years. But wait, you might say, maybe our age calculations are wrong? Maybe this galaxy is actually older than we think, just appears closer to the Big Bang due to some observational error? No, the redshift measurements, which tell us how far away, and thus how far back in time we're seeing these objects, are rock solid. Multiple independent techniques confirm these galaxies are genuinely from the early universe. Here's what will blow your mind. These early massive galaxies aren't just surprising in their existence. They're surprising in their maturity. Detailed spectroscopic analysis, led by teams including Roberto Maiolino at the University of Cambridge, reveals that these galaxies contain significant amounts of heavy elements, carbon, oxygen, nitrogen. Remember what I said earlier? Heavy elements come from supernova explosions of earlier generation stars. To have heavy elements, you need stars to have already lived their entire lives and died. Multiple generations of stars? Think of it like this. Imagine you discover an ancient city. You expect to find primitive stone dwellings, maybe some basic tools. Instead, you find skyscrapers with running water, electrical wiring, elevators, computers. And when you date the site, you find it's from 10,000 BC. That's not just surprising. That's cosmologically impossible, given what we understand about technological development. That's what these galaxies represent. They show a level of development that should take billions of years, appearing in a universe that's only a few 100 million years old. Some of these early galaxies are so bright, so massive, that astronomers initially couldn't believe the data. Ivo Lab at Swinburne University of Technology discovered what he termed universe breakers, galaxies so massive and so early that they contain more stars than should exist in the entire visible universe at that epoch, based on our models of matter density in the early cosmos. The technical term for these objects is impossibly massive high redshift galaxies. And yes, impossibly is the actual scientific term being used. That's how shocked the astronomical community is. But here's where we need to be careful, and this is important for understanding the scientific process. When I say these discoveries break our understanding, I don't mean every scientist has given up and decided cosmology is wrong. Science doesn't work that way. What's actually happening is more nuanced and, honestly, more interesting. Some teams are proposing that maybe these aren't galaxies at all, but rather supermassive black holes that are so active they're mimicking the appearance of star-filled galaxies. Others suggest that maybe the initial generation of stars was far more efficient at forming than we thought, accelerating the entire timeline. Still others wonder if dark matter, which we don't fully understand anyway, behaves differently in the early universe than it does today, causing matter to clump together faster. These are all reasonable scientific responses to anomalous data. Modify the model to fit the observations. Propose new mechanisms. Test predictions. But there's another possibility, one that most scientists are reluctant to speak about publicly, but whisper about in conference hallways. What if the Big Bang Theory itself needs fundamental revision? What if the universe didn't actually begin 13.8 billion years ago? What if there was something before, something that allowed time for these galaxies to form before we call the Big Bang? This isn't fringe speculation anymore. This is being discussed by mainstream cosmologists, published in peer-reviewed journals, and debated at major conferences. And it gets even stranger when we look at what else JWST is finding at the edge of the universe. Discoveries that compound the mystery and point towards something truly reality-shattering. But I'm getting ahead of myself. Before we go there, we need to understand exactly how we measure cosmic distances and cosmic time, because this is where the next revelation gets truly mind-bending. Let me ask you something that seems simple, but will reveal just how strange the universe really is. How far away is the edge of the universe? Your first instinct might be to say, well, if the universe is 13.8 billion years old, and light travels at a fixed speed, then the edge must be 13.8 billion light years away. That's logical. That's what most people would guess. And it's spectacularly wrong. The actual edge of the observable universe is approximately 46.5 billion light years away in all directions. Yes, you heard that right. The universe is less than 14 billion years old, but the edge is 46 billion light years away. How is that possible? How can something travel 3 times farther than it's had time to travel? The answer reveals one of the most counterintuitive aspects of cosmic reality. Space itself is expanding, and it's not expanding into anything. The distance between galaxies isn't increasing because the galaxies are moving through space. The distance is increasing because space itself is stretching. Think of it like baking raisin bread. Before you put the dough in the oven, you measure the distance between two raisins, let's say 1 inch. After baking, those same two raisins are now 3 inches apart. Did the raisins move? Not through the dough, no. The dough itself expanded, carrying the raisins along with it. This is crucial to understand because it means there's no center to the expansion. Every point in space sees every other point moving away. If you were in the Andromeda galaxy right now, you'd see the Milky Way moving away from you, and you'd see distant galaxies beyond us also moving away. The expansion is happening everywhere, all at once. And here's the kicker. Space can expand faster than the speed of light. Nothing can move through space faster than light. That's still true. But space itself isn't constrained by that limit. In the very early universe, during a period called cosmic inflation, which we'll discuss in detail later, space expanded so rapidly that regions separated by inches one moment were separated by billions of miles the next. This means that photons emitted from a galaxy 13 billion years ago have been traveling toward us all that time. But the galaxy itself has been carried away by the expansion of space. So while the light took 13 billion years to reach us, the galaxy that emitted is now much farther away, somewhere around 46 billion light years distant. This brings us to one of the most important concepts in modern cosmology, the cosmic light horizon. This is the fundamental limit on what we can observe, not because of telescope limitations, but because of the age of the universe itself. Light from anything farther than 46 billion light years away simply hasn't had time to reach us yet. The universe is only so old. That light is still on its way, perhaps arriving millions or billions of years from now, assuming the universe's expansion doesn't accelerate too much. So when we talk about finding galaxies at the edge of the universe, we're really talking about finding galaxies near our cosmic light horizon, seeing them as they appeared when the universe was just a tiny fraction of its current age. Now, how do we measure these enormous distances? How do astronomers know that a particular galaxy is 12 billion light years away versus 10 billion? This is where the magic of spectroscopy and redshift comes in. And understanding this will make the JWST discoveries even more shocking. When light passes through a prism, it splits into a rainbow of colors. Each chemical element, when heated, emits light at very specific wavelengths. Hydrogen emits light at particular wavelengths, helium at different wavelengths, oxygen at others. These wavelengths are like fingerprints, unique and unmistakable. When we capture light from a distant galaxy and split it into its component wavelengths, we see these same elemental fingerprints. But there's something strange. All the wavelengths are shifted toward the red end of the spectrum. They're stretched. A hydrogen line that should appear at 486 nanometers might appear at 600 nanometers instead. This redshift happens because the universe is expanding. As light travels through expanding space, its wavelength gets stretched along with the space. The farther the light travels, the more expansion it experiences, the more its wavelength gets stretched. So by measuring how much the spectral lines are redshifted, we can calculate how far the light has traveled, and thus how distant the object is. Astronomers use something called the redshift parameter, designated with the letter Z. A redshift of Z equals 1 means wavelengths have been stretched by a factor of 2. Z equals 2 means stretched by a factor of 3. The most distant confirmed galaxies discovered by JWST have redshifts around Z equals 13 or higher, meaning their light has been stretched by a factor of 14. These are the galaxies we're talking about. Galaxies with redshifts indicating they formed just 300 to 500 million years after the Big Bang. But here's where things get weird, and this is something that keeps cosmologists up at night. When we look at these incredibly distant, incredibly early galaxies with JWST, we see some with redshifts that push the boundaries of what should even be possible. We're seeing candidate galaxies, not yet fully confirmed, with redshifts of z equals 16, z equals 18, even potential candidates with z equals 20. Why is this a problem? Because at these redshifts, we're seeing the universe when it was only 150 to 250 million years old. At these epochs, the universe should still be in what's called the Dark Ages. This is the period after the cosmic microwave background was released, but before the first stars had formed and ignited. It's called the Dark Ages because there were no light sources yet. No stars, no galaxies, nothing but hydrogen and helium gas slowly collapsing under gravity. Finding not just stars but entire galaxies in this period is like finding a bustling city in a region that should be uninhabited wilderness. Adam Rees, who won the Nobel Prize for discovering that the universe's expansion is accelerating, recently stated in an interview that these JWST discoveries represent either a fundamental crisis in cosmology or an exciting opportunity to revise our understanding. Either way, we're standing at a pivotal moment in the history of astronomy. But to fully appreciate why these discoveries are so threatening to our cosmic timeline, we need to talk about something called the cosmic web, and how galaxies aren't randomly distributed throughout space, but follow a beautiful, terrifying structure that suggests the universe might be far older or far stranger than we ever imagined. And that's where the real mystery deepens, because the cosmic web itself tells a story of time, vast stretches of time that might not fit into our 13-point-8-billion-year timeline. Close your eyes and imagine the universe not as a collection of stars and galaxies scattered randomly through empty space, but as a vast three-dimensional spider web. Galaxies aren't the web. They're the dewdrops clinging to it. The web itself is made of dark matter, that mysterious substance that makes up 85% of all matter in the universe, but doesn't emit, absorb, or reflect light. This is the cosmic web, and it's one of the most beautiful and terrifying structures in existence. Here's what makes it so astounding. The cosmic web spans the entire observable universe. Filaments of dark matter, hundreds of millions of light years long, connect clusters of galaxies like cosmic highways. Where these filaments intersect, you find massive galaxy superclusters containing thousands of galaxies. Between the filaments are vast voids, enormous regions of space containing almost nothing, spanning hundreds of millions of light years. The cosmic web was first predicted mathematically in the 1980s, but it wasn't until the 2000s that we had the computational power and observational data to map it. Researchers like Volker Springel, who created the famous Millennium simulation, showed that this structure emerges naturally from the initial conditions of the Big Bang, shaped by gravity, acting over billions of years. And here's the critical point, forming this structure takes time. A lot of time? Think of it like city planning. You don't just get superhighways and interconnected metropolises overnight. First, you need people to settle in various locations. Then, over time, roads form between settlements. Successful settlements grow into towns, then cities. The cities develop connections, trade routes, major highways. Eventually, you get a complex network of interconnected urban centers separated by rural areas. This takes decades, centuries, even. The cosmic web is similar, just scaled up to cosmic proportions. After the Big Bang, matter was distributed almost uniformly throughout space. There were tiny density variations, quantum fluctuations that got stretched to cosmic scales during inflation. But these variations were only about 1 part in 100,000. That's incredibly smooth. Gravity amplifies these tiny variations over time. Regions slightly denser than average attract more matter, growing denser still. Matter flows along the path of least resistance, creating filaments. The filaments intersect, forming nodes where galaxy clusters form. Meanwhile, regions slightly less dense than average lose matter to the denser regions, becoming voids. This process is well understood. We can simulate it on computers. We can watch virtual universes evolve from smooth initial conditions to complex cosmic webs. And here's what every simulation shows. This process takes billions of years. You cannot rush it. Gravity acts at a fixed rate. Matter can only flow so fast. Structure builds gradually, hierarchically, from small to large. The cosmic web we observe in the local universe, the one around us, clearly shows the effects of billions of years of gravitational evolution. It's mature, developed, fully formed. So when JWST looks back to the early universe, astronomers expected to see a cosmic web in its infancy. Primitive filaments just beginning to form. Galaxies that haven't yet connected into larger structures. A universe still in the process of organizing itself. But that's not what they're finding. And this is where the story takes a turn into territory that makes even skeptical scientists wonder if something fundamental is wrong with our timeline. In 2023, a team led by Yoshihisa Asada at the University of Tokyo analyzed JWST data and found something astounding. Evidence of mature large-scale structure in the universe when it was less than 1 billion years old. They found correlations in galaxy positions that suggest these galaxies were already following the patterns of the cosmic web. Let me emphasize what this means. The cosmic web visible today took at least 5 to 6 billion years to develop its current structure. Yet here we're seeing similar structures when the universe was 7 times younger. It's like planting a garden and coming back the next day to find 100-year-old oak trees. Some galaxies JWST has discovered appear to already be part of protoclusters, groups of galaxies bound together by gravity. One such protocluster, discovered by Takahiro Morishita at IPAC, contains at least 7 galaxies in a relatively small region of space, all existing just 650 million years after the Big Bang. These galaxies aren't just near each other by chance. Spectroscopic analysis shows they're gravitationally bound, orbiting their common center of mass. Forming a gravitationally bound cluster requires multiple steps. First, the individual galaxies must form. Then, they must somehow find themselves in proximity. Then, gravity must have had time to bind them together into a coherent system. Each step requires time. The fact that this has already happened when the universe is less than 5% of its current age is deeply troubling to standard cosmological models. Rajendra Gupta, a physicist at the University of Ottawa, published a paper in 2023 proposing something radical. What if the universe is actually 26.7 billion years old, not 13.8? His model suggests that the early universe had different physical constants than we observe today, particularly in how light behaved. If light tired, losing energy over enormous distances in a different way than we think, it could make distant galaxies appear farther away and thus earlier than they actually are. Now, Gupta's model is controversial, and most cosmologists don't accept it. But the fact that it's being seriously discussed in scientific journals, the fact that the editor of a major physics journal thought it was worth publishing, tells you how desperate some scientists are to reconcile these observations with reality. Other researchers are exploring whether dark energy, the mysterious force accelerating the universe's expansion, might have behaved differently in the early universe. If dark energy was weaker back then, or even temporarily negative, it could have allowed structure to form faster than current models predict. But here's something that should make your brain hurt. Some of these early galaxies aren't just mature. They're dead. Spectroscopic analysis of certain galaxies from when the universe was only 700 million to 1 billion years old shows that they've already stopped forming stars. They're what astronomers call quenched galaxies. Their star formation has shut down completely. Why does this matter? Because galaxies don't just randomly stop forming stars. Quenching requires specific mechanisms. Maybe a supermassive black hole at the galaxy's center becomes so active it blows out all the gas, preventing new stars from forming. Maybe multiple galaxies collide and the collision somehow disrupts star formation. Maybe the galaxy simply runs out of cool gas to form new stars. All of these mechanisms take time. They require the galaxy to first form, then undergo significant evolution, then experience some dramatic event that shuts down star formation. To have this entire life cycle complete when the universe is less than a billion years old suggests a level of cosmic precocity that shouldn't be possible. Carl Glazebrook at Swinburne University found one such dead galaxy, which he nicknamed heavy metal, existing just 700 million years after the Big Bang. This galaxy had already lived through its entire active phase and retired. In human terms, it's like finding an 80-year-old person in a world where humans have only existed for 15 years. Now, I want to be very clear about something, because it's easy to get swept up in the sensationalism of these discoveries. Not every astronomer thinks the Big Bang theory is wrong. Many, probably most, think that we're simply missing something about how the early universe worked. Maybe star formation was dramatically more efficient in the early universe. Maybe the first generation of stars, called population 3 stars, were far more massive than we think, living and dying in just a few million years, and thus accelerating the production of heavy elements. Maybe dark matter interacts with normal matter in ways we haven't accounted for. These are all reasonable proposals, and teams of researchers are testing them with new simulations and observations. But there's a growing sense in the astronomical community that something bigger might be at play. Some of the brightest minds in cosmology are quietly considering possibilities that would have been dismissed as fringe just a few years ago. What if the Big Bang wasn't the beginning? What if it was just a phase transition in a much older, perhaps eternal universe? What if our observable universe is just one region in a vast multiverse, and the conditions we observe are local, not universal? What if time itself doesn't work the way we think at cosmic scales? These questions aren't just philosophical anymore. They're becoming scientifically necessary to explain what we're seeing. And the discoveries don't stop with impossibly mature galaxies and premature cosmic structure. There's something else JWST is finding at the edge of space and time, something even more bizarre than ancient galaxies. Something that suggests the universe might not be expanding the way we think it is. Let me tell you about the Hubble tension, because this is where things go from confusing to downright paradoxical. Remember Edwin Hubble's discovery that the universe is expanding? That discovery came from measuring how fast galaxies at different distances are moving away from us. The relationship is simple. The farther away a galaxy is, the faster it's receding. This relationship is captured in something called the Hubble constant, which tells us the rate of the universe's expansion. Here's the problem. When we measure the Hubble constant using nearby galaxies and other local methods, we get one number. When we measure it using the cosmic microwave background radiation and conditions in the early universe, we get a different number. And these two numbers don't agree. Adam Rees, who I mentioned earlier, has spent years refining measurements of the local expansion rate using a technique involving special types of exploding stars called Type Ia supernova. His measurements give a Hubble constant of about 73 kilometers per second per megaparsec. Don't worry about the units. Just focus on the number, 73. Meanwhile, measurements from the Planck satellite, which mapped the cosmic microwave background in exquisite detail, give a Hubble constant of 67. Again, just focus on the number, 67. 6.7 versus 73. That's almost a 10% difference. And before you think, what's the big deal? 10% isn't much. Let me explain why this is causing full-blown crisis in cosmology. Both measurements are incredibly precise. The uncertainty in each measurement is less than 1%. So we have two methods, both extremely accurate, both giving definitively different results. They can't both be right, which means either one method has some systematic error nobody has found, or, and this is the terrifying possibility, The universe doesn't behave the same way everywhere, or at all times. What if the universe is expanding at different rates in different regions? What if the expansion rate has changed over time in ways we don't understand? What if there's something fundamentally wrong with our understanding of cosmic distances? Enter the James Webb Space Telescope, which had the potential to solve this mystery. Researchers hoped that JWST's incredible precision would nail down the local expansion rate and resolve the tension. Instead, JWST made it worse. In 2024, teams using JWST to measure the same types of distance indicators Reese used confirmed his results. The local expansion rate really is around 73. The Hubble tension is real, not a measurement error. The universe is expanding faster in the local region than it should be based on the conditions in the early universe. But here's where JWST added a new wrinkle. When JWST at extremely distant galaxies, some of the most distant ever observed, it found evidence that the expansion rate might be different at different cosmic epochs. Some preliminary results suggest the universe might have expanded more slowly in the very early phases than our models predict. If confirmed, this is reality-breaking. It suggests the universe doesn't have a single, constant expansion rate. It accelerates and decelerates in ways we don't understand, driven by forces we haven't identified. Wendy Friedman at the University of Chicago, another leading expert on cosmic expansion, has suggested that the solution to the Hubble tension might require new physics. Not tweaks to existing theories, but genuinely new phenomena we haven't discovered yet. Maybe dark energy evolves over time. Maybe gravity works differently on cosmic scales than we think. Maybe the universe is more complex than our equations can capture. Now, combine the Hubble tension with the impossibly mature early galaxies, and a picture starts to emerge. A disturbing picture. What if the early universe was much older than we think? What if there was more time for galaxies to form, for structures to develop, precisely because the expansion rate was different? This brings us to one of the most radical ideas currently being discussed in cosmological circles, cyclical cosmology. The idea that the Big Bang wasn't the beginning, but rather the latest in a series of cycles of expansion and contraction. Imagine the universe expanding, then eventually contracting in a big crunch, then bouncing back in a new Big Bang, over and over, perhaps infinitely. In such a scenario, structure from previous cycles might survive through the bounce, giving the new universe a head start. Galaxies could form faster because the seeds for their formation were already present from a previous cycle. This sounds like science fiction, but it's being modeled by serious physicists like Paul Steinhardt at Princeton. Or consider another possibility. What if the Big Bang happened at different times in different places? What if our observable universe is just one bubble in an infinite multiverse, and different bubbles had their Big Bangs at different times? The galaxies we're seeing at the edge of our observable universe might actually be part of an adjacent bubble that's much older than our region. These ideas are speculative, but they're not crazy. They're grounded in serious theoretical physics and are being explored because the observations demand explanation. What JWST has done is drag these ideas from the fringes of theoretical physics into the mainstream of observational astronomy. We're not just speculating anymore. We're looking at data that doesn't fit our models, and we're being forced to consider radically new possibilities. And if you think this is as weird as it gets, wait until you hear what JWST is finding about the very first stars and black holes. Because those discoveries suggest that the laws of physics themselves might have been different in the early universe. Let me introduce you to a problem so profound that when it was first discovered, many astronomers simply didn't believe it was real. It's called the supermassive black hole formation problem, and it's been lurking in the background of cosmology for years, quietly troubling theorists. JWST has now thrust it into the spotlight, making it impossible to ignore. Here's the problem in its simplest form. Supermassive black holes shouldn't exist. Not that they shouldn't exist at all. We know they're real. There's one sitting at the center of our Milky Way galaxy with a mass 4 million times that of our Sun. The problem is that they shouldn't exist when they do. Specifically, they shouldn't exist in the early universe, less than 1 billion years after the Big Bang. But they're there. JWST is seeing them. And nobody understands how. Let me build up to why this is so bizarre. Black holes form when massive stars die. When a star at least 20 to 30 times the mass of the Sun exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses catastrophically in a fraction of a second, and if enough mass is involved, the collapse doesn't stop. It continues until a black hole forms, a region of spacetime where gravity is so intense that not even light can escape. These stellar mass black holes typically have masses ranging from a few times the Sun's mass up to maybe 100 solar masses. They're impressive objects, but they're tiny compared to supermassive black holes, which have masses of millions or even billions of solar masses. So how do supermassive black holes form? The obvious answer is that they start as stellar mass black holes and then grow by accumulating more mass over time. They can swallow nearby gas, dust, and even entire stars. They can merge with other black holes when galaxies collide. Given enough time, billions of years, a small black hole could grow into a supermassive one. This gradual growth model worked fine until we started finding supermassive black holes in the distant universe, existing when the universe was very young. The farther back we looked, the younger and more massive these black holes appeared to be. It was puzzling, but perhaps explainable if these black holes were just really efficient at gathering matter. Then JWST started operating, and the problem exploded. JWST has discovered supermassive black holes, some with masses over 1 billion times the Sun's mass, existing just 500 to 700 million years after the Big Bang. One particular black hole, discovered in 2023 by a team including Rebecca Larson at the University of Texas, has a mass estimated at several million solar masses, and exists when the universe is just 470 million years old. Here's why this is impossible. Even if a stellar mass black hole formed immediately after the Big Bang, say 100 million years after, and even if it accreted matter at the maximum physically possible rate, called the Eddington limit, it could not grow to 1 billion solar masses in just 400 million years. The math doesn't work. There simply isn't enough time. When matter falls into a black hole, it heats up and radiates energy. This radiation creates an outward pressure that pushes against infalling matter. At some point, the outward radiation pressure equals the inward gravitational pull, and accretion stops. This is the Eddington limit, and it sets a strict boundary on how fast a black hole can grow. Even at the Eddington limit, continuously feeding without any breaks, a stellar mass black hole would take over 1 billion years to reach 1 billion solar masses. But these black holes are appearing in half that time or less. So either our understanding of black hole growth is wrong, or these black holes didn't start out as stellar mass objects. They somehow formed directly as massive black holes, skipping the stellar death phase entirely. This is what's called the direct collapse scenario. Instead of a single massive star collapsing, an entire cloud of gas containing tens of thousands or hundreds of thousands of solar masses collapses directly into a black hole. This would create what's called a seed black hole, much more massive than stellar mass black holes, giving it a head start on growth. But direct collapse requires very specific conditions that are extremely rare. The gas cloud must be very pure, containing almost no heavy elements, because heavy elements would cause the cloud to fragment into individual stars before it could collapse as a whole. The cloud must also be kept hot enough to prevent fragmentation, but not so hot that it disperses. These conditions might exist in the very early universe, but they'd be uncommon. So maybe we'd see a few of these massive seed black holes. But JWST is finding them seemingly everywhere. Wherever it looks in the early universe, there are supermassive black holes. This suggests they're not rare flukes, but common features of the early cosmos. Priyamvada Natarajan at Yale University, one of the leading experts on black hole formation, has proposed that maybe these aren't black holes from collapsed stars at all. Maybe they're primordial black holes, formed in the first fractions of a second, after the Big Bang from density fluctuations in the early universe. These could have any mass, from microscopic to supermassive, depending on the size of the fluctuation. If primordial black holes formed in large numbers in the early universe, and if some of them were already quite massive, then they could serve as seeds for supermassive black holes, solving the timeline problem. But here's the issue. We have no direct evidence that primordial black holes exist at all. They're a theoretical possibility, but we've never observed one. Using them to explain another mystery is, as scientists say, multiplying hypotheses. It's solving one unknown with another unknown. There's another deeply weird possibility that some physicists are exploring. What if the fundamental constants of physics were different in the early universe? What if gravity was stronger, or the speed of light was different, or the laws governing nuclear fusion operated differently? If the early universe had different physics, stars could have been much more massive, living much shorter lives, and collapsing into much more massive black holes. The entire stellar life cycle could have been accelerated, producing supermassive black holes in a fraction of the time it would take under current physics. This idea, called varying constants, is extremely controversial because it undermines the foundational assumption of physics, that the laws of nature are universal and unchanging. But some versions of string theory and other advanced physics theories do allow for constants to vary under certain conditions. João Magueo at Imperial College London has done extensive work on varying speed of light theories, showing how a faster speed of light in the early universe could solve several cosmological problems, including the supermassive black hole formation problem. If light traveled faster, energy could propagate faster, processes could happen faster, and the universe could effectively age faster than its chronological age would suggest. This sounds wild, but remember, we're trying to explain observations that don't fit any conventional theory. At some point, if the conventional theories keep failing, we have to consider unconventional ones. Now, here's where this connects back to the mature galaxy problem. Supermassive black holes and galaxies co-evolve. There's a tight relationship between the mass of a galaxy's central black hole and the mass of the galaxy's bulge. They grow together, influencing each other through feedback processes. If galaxies in the early universe already have supermassive black holes, it means the galaxies themselves must have already undergone significant evolution. You can't have a billion solar mass black hole without a surrounding galaxy that's also massive and mature. The two go hand in hand. So the mature galaxy problem and the supermassive black hole problem aren't separate mysteries. They're two faces of the same cosmic enigma. The early universe is too developed, too evolved, too mature for its age. And there's one more discovery I need to tell you about. Something JWST found that might be the most important clue of all. Something about the very first light in the universe. Before we go further, I want you to do something for me. If you're finding this mind-bending and fascinating, hit that subscribe button. We're going deeper than any documentary has gone before, and you don't want to miss what's coming next. Also, leave a comment with your biggest question so far. What's the part of this that breaks your brain the most? I read every comment, and I love seeing where people's minds go with this material. Now, let's talk about the cosmic microwave background, because this is where everything connects and where the most profound implications emerge. The cosmic microwave background, or CMB, is the oldest light in the universe. It's the afterglow of the Big Bang, radiation that's been traveling through space for 13.8 billion years. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, filled with a plasma of charged particles that scattered light constantly. After this moment, called recombination, the universe became transparent. Light could suddenly travel freely through space. The CMB is that first light, the light released at the moment the universe became transparent. It's been traveling ever since, cooling and redshifting as the universe expands. Until today, it reaches us as microwave radiation with a temperature of 2.7 Kelvin. The CMB is incredibly important because it's a snapshot of the universe in its infancy. By studying the tiny variations in the CMB's temperature across different directions in the sky, scientists can learn about the conditions in the early universe, the density variations that would eventually become galaxies, and the cosmic web. The CMB has been studied in extraordinary detail by satellites like COBE, WMAP, and Planck. These missions produced maps showing temperature variations at the level of 1 part in 100,000. These tiny variations, called anisotropies, match the predictions of Big Bang theory with stunning precision. The CMB is often called the smoking gun evidence for the Big Bang. But here's something that doesn't get mentioned often enough. The CMB tells us about the universe at 380,000 years old. It doesn't tell us anything about what happened before that moment. The universe before recombination is hidden from us, obscured by the opaque plasma that filled space. This means there's a gap in our observational knowledge. We have the CMB showing us the universe at 380,000 years. Then we have the earliest galaxies and black holes. JWST is seeing it around 300 to 500 million years. Between those 2 points, we have very little direct observational data. This gap is where the mystery might hide. Something happened in those first few 100 million years, something that allowed galaxies and black holes to form much faster than our models predict. And we can't see it directly. Or can we? There's a theoretical possibility that might let us probe even earlier than the CMB. It's called the cosmic neutrino background, and it would have been released when the universe was just 1 second old. Neutrinos are ghostly particles that barely interact with matter. They were created in enormous numbers in the Big Bang, and they should still be permeating the universe today, even older and colder than the CMB. If we could detect the cosmic neutrino background, it would give us a glimpse into the universe at 1 second old, bridging part of that observational gap. But neutrinos are incredibly difficult to detect. No experiment has yet managed to observe the cosmic neutrino background, though there are proposals for how to do it. There's an even more tantalizing possibility: gravitational waves from the early universe. Gravitational waves are ripples in spacetime itself, created by violent cosmic events. Unlike light, gravitational waves can travel through the opaque early universe. If there were dramatic events in the first moments after the Big Bang, inflation, phase transitions, maybe collisions with other universe bubbles, they would have generated gravitational waves that are still propagating through space today. Detecting these primordial gravitational waves is one of the holy grails of cosmology. Several experiments, including LIGO, Virgo, and the planned LISA space-based observatory, are searching for them. If found, these gravitational waves would let us observe the universe in its first trillionth of a second, long before even the neutrino background. But we don't have these observations yet. We have the CMB, and we have JWST's observations of the universe after 300 million years. And here's the crucial point. The CMB looks exactly like standard Big Bang theory predicts. The tiny temperature variations, their statistical distribution, the overall spectrum, everything matches. The CMB tells us the universe at 380,000 years old was smooth, homogeneous, and evolving exactly as expected. So how do we reconcile this? The CMB says everything is normal. JWST says everything is weird. Both can't be fully right. This is where some really creative thinking is happening. Hiranya Paris at University College London has suggested that maybe the initial conditions of the universe, the quantum fluctuations that got stretched during inflation, are slightly different than we've assumed. Maybe there were more large-scale fluctuations than small-scale ones, which would allow big structures to form faster without contradicting the CMB data, which is more sensitive to small-scale fluctuations. Others propose that dark matter might have had a more complex interaction with normal matter in the early universe than we think. Maybe dark matter and normal matter were more tightly coupled, allowing structures to grow faster before they decoupled. Still others wonder if there was a period of enhanced star formation efficiency in the very early universe. Maybe the first stars were able to convert gas into stars much more efficiently than stars today, rapidly building up galaxies. All of these are attempts to tweak the standard model, to adjust parameters within the existing framework. But there's a growing sense that tweaks might not be enough. We might need a paradigm shift. And this brings me to what I think is the most important realization from all of JWST's discoveries. The universe is telling us that we don't understand cosmic time as well as we thought we did. Let's talk about time, because this is where the implications of JWST's discoveries become truly profound. When we say the universe is 13.8 billion years old, what do we actually mean? We mean that 13.8 billion years have passed since the Big Bang, according to a clock that's been moving along with the average expansion of the universe. But here's something that Einstein's theory of relativity tells us. Time is not absolute. Time flows at different rates depending on motion and gravity. If you're moving at high speed relative to someone else, time passes slower for you than for them. If you're in a strong gravitational field, time passes slower for you than for someone in a weaker field. This isn't science fiction. This is experimentally verified fact. GPS satellites have to account for relativistic time dilation, or they'd give incorrect positions. Now, in the early universe, conditions were extreme. Matter was densely packed. Velocities were high. Gravitational fields were intense. Could time have flowed differently than it does today? Standard cosmology assumes that time has flowed uniformly since the Big Bang, but this assumption might not hold under all conditions. Some physicists are exploring whether time itself has varied over cosmic history. João Magueo, who I mentioned earlier, proposes that in the very early universe, the speed of light was much faster than it is today. If true, this would mean that physical processes, which are limited by the speed of light, could have proceeded much faster in the early universe. A few 100 million years of cosmic time might have been enough for processes that would take billions of years today. This would solve many of the mysteries. Galaxies could mature faster. Black holes could grow faster. Structure could form faster. Not because the processes themselves are different, but because time itself was effectively running faster due to a higher speed of light. Other researchers are exploring whether the rate of cosmic expansion itself has varied in more complex ways than we think. We know the expansion has varied, first accelerating during inflation, then decelerating under gravity, then accelerating again under dark energy. But maybe there were additional phases, periods where the expansion temporarily slowed or reversed, giving structures extra time to form. Michael Turner at the University of Chicago, one of the pioneers of dark energy research, has noted that dark energy might not be a cosmological constant as Einstein proposed. It might be a dynamic field that changes over time. If dark energy was much weaker in the early universe, or even negative, meaning it caused attraction rather than repulsion, it could have allowed matter to clump together much faster. All of these ideas point to the same conclusion. Cosmic time is more complex than a simple linear progression from the Big Bang to now. The age of the universe might be a more subtle concept than we realized. And here's something that should really bend your brain. What if different regions of the universe have aged at different rates? In Einstein's relativity, there's no universal clock. Every observer has their own clock, and those clocks can tick at different rates depending on conditions. On Earth, we experience time at a particular rate determined by our velocity and the gravitational field we're in. If we could somehow observe the universe from a location with very different conditions, near a black hole, for instance, or moving at nearly the speed of light relative to us, we would see cosmic history unfold at a different pace. Now, in the early universe, the density of matter varied from place to place. Remember the tiny fluctuations that would become galaxies. Could these density variations have caused time to flow at different rates in different regions? Could some regions have effectively aged faster, allowing galaxies to mature more quickly there? This is speculative, cutting-edge theoretical territory, but it's the kind of thinking that JWST's discoveries are forcing cosmologists to consider. There's a deeper philosophical question lurking here too. What do we mean when we say the universe has an age? We're measuring age based on the physics we observe today. But if physics was different in the past, if constants varied, if time flowed differently, then is our measurement even meaningful? It's like trying to measure the age of a tree using its growth rings, but not knowing that the tree grew much faster in its youth than it does now. You'd count the rings and get an answer, but that answer wouldn't reflect the actual time elapsed. Lee Smolin, a physicist at Perimeter Institute, has written extensively about the nature of time in cosmology. He argues that time is more fundamental than we typically assume, and that the laws of physics themselves might evolve over time. If true, the early universe might have operated under somewhat different laws than we see today, laws that allowed for faster structure formation. This is borderline metaphysical, but it's grounded in serious physics and mathematics. And the reason it's being discussed is because the observations demand it. We have to explain what we're seeing, and conventional explanations aren't cutting it. So where does all this leave us? What's the actual answer to what NASA found at the edge of the universe? Here's the honest truth. We don't fully know yet. The data is still being analyzed. New observations are being made. Theories are being developed and tested. We're in the middle of a scientific revolution in cosmology, and revolutions are messy. It takes time for clarity to emerge. But we can say some things with confidence. We can say that the universe is stranger and more complex than we thought. We can say that our understanding of the early universe is incomplete. We can say that time in physics might be more flexible than we assumed. And we can say that the simple, elegant story of the Big Bang is being replaced by something richer, weirder, and ultimately more profound. Before we get to the really mind-bending implications of all this, I want to connect you personally to these discoveries. Because this isn't just abstract science happening in some distant observatory. This is fundamentally about you, your existence, your place in the cosmos. I want you to stop for a moment and think about your own existence. You are a collection of atoms, carbon, oxygen, hydrogen, nitrogen, iron, organized in a stunningly complex pattern that can think, feel, and wonder about the universe. Every atom in your body, except for hydrogen, was forged in the heart of a star. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was created by nuclear fusion in stellar cores, then scattered into space when those stars exploded. You are literally made of stardust. Carl Sagan said that, and it's beautifully true. But here's what makes JWST's discoveries personally relevant. Those atoms in your body came from stars that lived and died billions of years ago. The heavy elements in your body required generations of stars to produce. First-generation stars made some heavy elements. Second-generation stars made more. Third-generation stars made even more. Our sun is at least a third-generation star, maybe fourth or fifth, and it formed from a cloud of gas enriched by the deaths of previous stars. For you to exist, there had to be enough time for multiple generations of stars to live their full lives. There had to be enough time for planetary systems to form. There had to be enough time for complex chemistry to develop on at least one planet. There had to be enough time for life to emerge and evolve into beings capable of contemplating their own existence. All of this takes time. Billions of years. The standard timeline of the universe gives us just barely enough time for all of this to happen. Earth is 4.5 billion years old. Life appeared almost immediately, at least in simple form. But complex life took much longer. Animals have only existed for about 600 million years. Humans have only existed for a few 100,000 years. And technological civilization capable of building space telescopes has only existed for a few decades. We are the latest products of the 13.8 billion year process of cosmic evolution. We're just barely possible within the timeline we have. Now, here's the twist that JWST introduces. If the early universe was more developed than we thought, if galaxies and stars formed faster than we believed, then complex chemistry could have started earlier. Planets could have formed earlier. Life could have emerged earlier. There might have been civilizations billions of years ago, when the universe was just a couple billion years old, long before Earth even existed. Civilizations that rose, flourished, and perhaps fell, leaving no trace we could detect from our remote vantage point. Think about how recently humans developed technology. A mere 10,000 years ago, we were hunter-gatherers. 100 years ago, we didn't have computers. 50 years ago, we landed on the moon. Today, we have space telescopes observing the edge of the universe. Imagine a civilization that had a billion-year head start. What might they have achieved? Could they have mastered physics to the point of manipulating space-time itself? Could they have spread throughout galaxies, even galaxy clusters? Could they have developed technology so advanced it would appear magical to us? This isn't idle speculation. If JWST's discoveries are correct, if the universe allowed for earlier structure formation, then we have to take seriously the possibility that we're not the first. We might not even be among the earliest. SETI, the search for extraterrestrial intelligence, has been searching for radio signals from alien civilizations for decades. So far, we've found nothing. But maybe we're looking in the wrong places, or in the wrong ways. A civilization a billion years more advanced than us might not use radio waves at all. They might communicate using technologies we can't even imagine. Or here's a darker possibility. Maybe civilizations don't last. Maybe there's something we call it the Great Filter, a challenge that civilizations typically fail to overcome. Maybe most civilizations destroy themselves through war, or environmental collapse, or technological mishap before they become truly advanced. If the universe is older and more developed than we thought, and we still don't see evidence of other civilizations, it might suggest that the Great Filter is real and formidable. It might suggest that we're approaching it ourselves, and we need to be very, very careful. Or maybe, just maybe, we're special. Maybe despite the vast age and size of the universe, despite the possibility of countless other worlds, we're the ones who made it to this point of self-awareness and technological capability. Maybe we're the universe's way of understanding itself. But let's go deeper. Let's talk about the nature of reality itself, because JWST's discoveries touch on something even more fundamental than just the age and development of the universe. They touch on the nature of existence, consciousness, and meaning. The standard Big Bang model gives us a universe with a clear beginning and a likely end. It started in a singularity, expanded, evolved, and will eventually either expand forever into cold, dark emptiness, or collapse back in a big crunch. Either way, there's a finality to it. The universe is a temporary thing, existing for a finite time in a finite form. But if the Big Bang wasn't the beginning, if there were cycles before ours, or if our universe is part of an eternal multiverse, then suddenly the cosmos takes on a very different character. It's no longer a temporary phenomenon. It's an eternal, perhaps infinite, structure. And we're just one small part of it? What does that mean for meaning? If the universe is eternal, if everything that can happen does happen somewhere in the infinite expanse, then does anything we do matter? Are we just a brief eddy in an infinite ocean, significant to ourselves, but ultimately inconsequential in the cosmic scheme? Or is the opposite true? Maybe the fact that we exist, that consciousness has emerged, that matter has organized itself into patterns capable of understanding and appreciating the universe. Maybe that's the most significant thing that can happen. Maybe we're the universe becoming self-aware, and that's not inconsequential. That's miraculous. Viktor Frankl, a psychologist and Holocaust survivor, wrote that humans need meaning to survive. We need to believe that our existence matters, that our actions have significance. The cosmos as revealed by modern science can seem cold and indifferent, but maybe we're looking at it wrong. Yes, we're small. Yes, we're temporary. Yes, the universe is vast beyond comprehension, but we're here. We exist. We can think, feel, love, create, explore. We can build telescopes and peer to the edge of space and time. We can unravel the mathematical structure of reality. We can make art and music and literature. We can care for each other. Doesn't that count for something? Doesn't that make us, in a very real sense, the most important thing in the universe, because we're the part that cares, that assigns value, that creates meaning? The universe doesn't care about anything. It can't. It's not conscious, but we care. And in a universe that can't care, the beings that can care are infinitely precious. JWST's discoveries, by showing us that the universe is stranger and more complex than we thought, remind us that we still have so much to learn. We don't have all the answers. We might never have all the answers. But the search itself, the quest to understand, that's what makes us human. That's what makes us special. And here's something I want you to really absorb. You're participating in this grand quest right now. By watching this video, by engaging with these ideas, by thinking about the cosmos and your place in it, you're continuing a tradition that goes back to the first humans who looked up at the night sky and wondered what those lights were. You're part of an unbroken chain of curiosity and wonder, stretching back tens of thousands of years and forward into the unknowable future. Every person who's ever gazed at the stars and asked, "What's out there?" is connected to you. And you're connected to everyone who will ever ask that question in the future. That's not nothing. That's everything. Now, I want to take you even deeper. I want to talk about what these discoveries mean for the fundamental nature of reality, because we're approaching territory where science and philosophy blur together, where the questions become as important as the answers. Let's start with a simple question that has profound implications. Why is there something rather than nothing? This is one of the oldest and deepest questions in philosophy. Why does the universe exist at all? Why is there matter, energy, space, time, rather than just ... nothing? The Big Bang Theory doesn't really answer this question. It tells us the universe began in a hot, dense state 13.8 billion years ago, but it doesn't tell us why. What caused the Big Bang? What came before it? Why did it happen? Some physicists have proposed that the universe could have come from nothing, that quantum fluctuations in the vacuum of space could spontaneously create matter and energy. Lawrence Krauss wrote a whole book about this, A Universe from Nothing. But critics pointed out that the quantum vacuum isn't really nothing. It's a something with properties and laws. So the question just shifts. Where did the quantum vacuum come from? Others say maybe the universe has always existed in some form. Maybe there was no beginning. Maybe existence itself is eternal and necessary. But this doesn't really answer the question either. It just asserts that existence needs no explanation, which feels unsatisfying. Now, what JWST has done is complicate this question even further. By showing us that the early universe was more developed than expected, possibly suggesting time or physics worked differently back then, JWST has opened the door to even more fundamental uncertainty about cosmic origins. What if the Big Bang was not a beginning, but a transition? What if there was a previous universe that collapsed and rebounded? What if time itself doesn't have a beginning or end, but loops back on itself? What if our universe is constantly being created and destroyed, flickering in and out of existence in cycles we can't perceive? These aren't just wild speculations. These are serious theoretical models being developed by physicists. Roger Penrose, who won the Nobel Prize for his work on black holes, has proposed a cyclical cosmology model called conformal cyclic cosmology. In his model, the universe goes through infinite cycles, each beginning with something like a Big Bang and ending with a state that becomes the Big Bang of the next cycle. If something like this is true, then the question, why is there something rather than nothing, might not have an answer, because there never was nothing. There's always been something cycling eternally, without beginning or end. Or consider the multiverse hypothesis. This idea, which comes from several different areas of physics, including string theory and eternal inflation, suggests that our universe is just one bubble in an infinite foam of universes. Each bubble has different properties, different physical constants, different laws of nature. In this scenario, every possible universe exists somewhere in the multiverse. There are universes where the electron has a different charge, universes where gravity is stronger or weaker, universes where stars can't form, universes where life is impossible, and universes like ours where conditions are just right for complexity and consciousness to emerge. If the multiverse is real, then our existence is explained by selection bias. We observe a universe compatible with our existence because we couldn't exist in universes that aren't compatible. This is called the anthropic principle, and it's deeply controversial because it seems to give up on finding a deeper explanation. It says, things are the way they are, because if they were different, we wouldn't be here to observe them. But maybe that's the best answer we can get. Maybe the universe doesn't have a deeper purpose or explanation. Maybe it just is, or maybe the answer is even stranger. Some physicists and philosophers have seriously proposed that consciousness might play a fundamental role in reality. Not in a mystical sense, but in a precise quantum mechanical sense. Quantum mechanics tells us that particles exist in superposition, multiple states at once, until they're observed or measured. The act of observation seems to collapse the superposition into a definite state. But what counts as an observation? Does it require a conscious observer? If so, does that mean consciousness is somehow fundamental to the structure of reality? This is called the observer effect, and it's one of the most debated aspects of quantum mechanics. Different interpretations of quantum mechanics handle it differently. The Copenhagen interpretation suggests that observation does play a special role. The many worlds interpretation says that all possibilities exist in parallel universes, and observation just determines which branch we find ourselves in. But here's a wild thought. What if the universe requires observers to exist? What if consciousness is not just a byproduct of complex matter, but a necessary component of reality itself? What if, in some deep sense, the universe exists because we observe it? John Wheeler, one of the greatest physicists of the 20th century, proposed something called the participatory anthropic principle. He suggested that observers, by making observations, retroactively bring the universe into existence. It sounds like mystical nonsense, but Wheeler wasn't a mystic. He was one of the architects of quantum mechanics and general relativity. Wheeler imagined the universe as a self-excited circuit. Observations now affect the past through quantum effects, and the past leads to the present, creating a loop where the universe and consciousness are bound together, each necessary for the other. If something like this is true, then you, right now, watching this video, thinking about these ideas, you're not just passively observing the universe. You're actively participating in its existence. Your consciousness is part of what makes reality real. I know this sounds crazy. I know it's hard to wrap your head around, but quantum mechanics is weird, and the universe is weirder than we can possibly imagine. The fact that JWST is finding things that don't fit our models reminds us that we don't have reality figured out. We're still scratching the surface. And that's exciting. That's hopeful. Because it means there's still so much to discover. So many mysteries yet to unravel. We're not at the end of science. We're barely at the beginning. Let's bring this back to something more concrete, because I don't want you to leave feeling like everything is uncertain and unknowable. There are things we do understand. There are discoveries that are solid and real. And there are practical implications of JWST's, observations that matter for our future. First, the technology itself. The James Webb Space Telescope is an engineering marvel. It took decades to design and build. It cost $10 billion. It had to be folded up to fit inside a rocket, launched 1 million miles from Earth, then unfold itself perfectly in space with no chance for human repair. And it worked. That's an astounding achievement of human ingenuity. The technology developed for JWST, the infrared detectors, the mirror alignment systems, the heat management, all of it has spin-off applications here on Earth. Better medical imaging devices, more efficient solar panels, advanced materials for thermal control. Whenever we push the boundaries of what's possible in space, we end up advancing technology on Earth too. Second, the science. Regardless of how we ultimately explain JWST's discoveries, we're learning real, concrete things about the universe. We're mapping the distribution of galaxies with unprecedented detail. We're measuring the chemical composition of early galaxies, learning how elements were produced. We're discovering planets around other stars, some of which might be habitable. We're observing the formation of stars and planetary systems in real time. All of this data will be studied by astronomers for decades. Papers are being written right now, analyzing JWST observations. Careers are being built on this data. Students are learning astrophysics by working with these images. The scientific return on JWST will continue for the rest of our lives. Third, the inspiration. Millions of people around the world have seen JWST's images. Children have looked at those pictures of distant galaxies and decided they want to become astronomers or physicists. Adults have rediscovered their sense of wonder about the universe. People have been reminded that there's more to existence than daily worries and routines. This might sound soft and unmeasurable, but it's real. Inspiration matters. A sense of wonder matters. Feeling connected to something larger than ourselves matters. These are the things that make life meaningful, that motivate us to learn and grow and create.